Welcome back to the video on the ether, which is a part of the third semester organic chemistry for BSc students in the Mysore University. Let us learn what are ethers. Ethers are the organic compounds in which two alkyl or aryl groups are attached to a divalent oxygen. They are represented by the general formula ROR, where R may be an alkyl or a aryl group. For example, dimethyl ether is a classical example for the functional group ether. Here we have a divalent oxygen which is attached to two alkyl group which can be the same. For example, in the dimethyl ether, we have two methyl group attached to the oxygen atom. And another example, the diethyl ether, where the divalent oxygen is bonded to two ethyl groups on either side. So, the ethers are the organic compound where we have two alkyl or an aryl group attached to a divalent oxygen. And the ether, as said, is a class of an organic compounds which contain the ether group, and the ether group can be represented as ROR. For the simplest ether, for example, here we take the dimethyl ether where the oxygen on either side have a methyl group, and the type of the hybridization is sp3, and the bond angle being the 111 or 111 degrees. And this is the bond stick model representation of the ether. Coming to the classification of ether, we can classify the ether based on the nature of the groups that have been attached to the oxygen. When they are alkyl group, we designate them to be as aliphatic ether, and when we have an aromatic group, we call it by the name aromatic ether. So, for example, an aliphatic butyl methyl ether. So we have a butyl on one side and ether group on the other side of the oxygen, and it is an example for an aliphatic ether. Coming to the aromatic ketone, we have a phenyl group or which is bonded to the oxygen, and on the other side we have a methyl. So we have an alkyl and an aryl group, and an example for an aromatic ether. We can also have two aromatic groups bonded to the divalent oxygen. For example, diphenyl ether is an example for an aryl ether. Coming to the types of the ether, we have simple ether, or we can also call them to be the symmetrical ether. When the alkyl or the aryl groups attached to the oxygen atom are the same, we designate them to be the simple ether or the symmetrical ether. So, dimethyl ether, diethyl ether are the example for the simple ether. Next class is the mixed ether, and it is also called as unsymmetrical when the alkyl or the aryl groups are different, and here we represent them ROR dash. For example, in the ethyl methyl ether, we have a methyl group on one side and ethyl group on the other side. So it is an mixed or an unsymmetrical ether. So likewise, we can have an alkyl group on one side of the oxygen and also the aryl group on the other side, and we call to be the methyl phenyl ether. The ether are further classified as open chain, cyclic, saturated, unsaturated, aromatic ether depending on the nature of the groups that is attached to the group, that is the oxygen atom. So when we come to the ethers, This ether may be considered as the derivatives of water in which both the hydrogen atoms has been replaced by an alkyl group. They may also be considered to be the derivatives of alcohol in which the hydroxyl hydrogen has been replaced by an alkyl group. So the ethers can be either derivatives of the water or the alcohol. In the case of the water, the hydrogen atoms bonded to the oxygen are replaced by an alkyl or an aride when they are considered as the derivatives of the alcohol. Here, the hydrogen that has been attached to the oxygen is replaced by an alkyl group. So, when we come to the nature of your ether, the ether is linked to the alkyl groups on either side and comparatively it is an inert. However, due to the presence of a lone pair of electron on the oxygen, it behaves like Lewis base and form the addition compounds with the mineral acid. Coming to the nomenclature of the ether, as we know, there are two systems. The first we generally is the common name or the trivial system, and the other is the IPR system. Coming to the common name system, in this system of nomenclature, the ethers are named according to the alkyl or aryl group attached to the oxygen atom, and the word ether is placed after it. So let us take an example here. So here we have two methyl group and hence I use a prefix dimethyl and later I place the word ether and give the name to be the dimethyl ether. So when I have an ethyl group, I call it by the name diethyl ether. So this is the nomenclature with respect to the simple ether. So they are named as dialkyl ether when the two alkyl groups are the same, as we have taken the example of dimethyl ether and diethyl ether. However, this is not the same situation in all the types of ether. We can have two different type of alkyl groups or we can have an alkyl group and an aryl group. So when the alkyl groups are different, they are named alphabetically. For example, here we have an ethyl and we have a methyl. Alphabetically, E comes the first, and hence we designate this to be the ethyl, methyl, ether. The same is also true with this example. Here we have a butyl group and a methyl group, and here it is called as tertiary butyl methyl ether. So when I take an alkyl aryl ether, we have an ethyl and a phenyl group. We call it to be ethyl phenyl ether. So these are the few examples for the nomenclature of ether according to the common name system. Coming to the nomenclature of ether, according to the IPR system, so this is the functional group where this oxygen we designate to be the etheric oxygen which is flanked on either side by an alkyl or an aryl which can be same or different. So according to the IPR system, we name the ether as alloxyalkane. So the smaller group with the oxygen is taken as alloxy group and the larger group is taken as the parent alkane. So once again I repeat, in the IPA system, we consider the ethers to be alloxy alkane and here the smaller group with the oxygen is taken as the alloxy group and the larger group is taken as the parent alkane. So let us take this example where we have two methyl groups. Since it is a symmetrical, so we consider to be the CH3 to be the methoxy and the C methyl group to be the parent alkane and we give the name methoxymethane. The same is also true with the ethoxyethane, which is an example for a symmetrical ether. So we have the two alkyl groups to be the same. So we take one the for ethane to be the ethoxy and ethane and we name to be the ethoxyethane. But when we are going to name an unsymmetrical ether, let us look for example in this case we have a methyl group and an ethyl group which is attached to the functional group oxygen. So as I said, they are designated as alloxyalkane and the smaller group with the oxygen is to be considered as alloxy group and hence here the methyl group is the smaller compared to the ethyl group and hence we take the methyl group as the alloxy group and give the name the methoxy followed by the larger group where we take them to be as a parent alkane. So we have an ethane. So we name this ether to be methoxyethane. So once again I repeat, the smaller group will be considered as an alloxy and it will be given the oxy as the name and the bigger group is considered to be the parent alkane. So the another example here we have a methyl group and a benzene group. So here since we have only one carbon atom in the methyl, it is the smaller group and we consider to be the alloxy and we name it as a methoxy followed by the larger group as the parent alkane and hence the name of this is methoxybenzene. So these are the few examples which I have taken for the nomenclature. So here I have given a list of the ether containing compounds, a common name and the IPR name. So let's just recall. So the compound is CH3OCH3. So we call it to be dimethyl ether as a common name and methoxymethane to be the IPR name. Likewise, the compound C2H5O C2H5 it is called diethyl ether ethoxyethane and the other example here is methyl and propyl ether 1-methoxypropane. Likewise, let us take a few examples for alkyl aride. So we have a C6H5O CH2 6 CH3. So we have an eptyl attached to an oxygen on one side and a phenyl. So the trivial system is the heptyl phenyl ether and the IPR being the so when I compare with the heptane, here the phenyl has 6 carbon atoms. So this is the smaller group and hence I give the or alloxy to the smaller and I call this to be 1-phenoxy and the bigger group I retain to be the parent alkane and hence the name is 1-phenoxyheptane. So these are the other examples for the ether. So coming to the synthesis of the ether, and in the synthesis of the ether, we are going to learn how ether are synthesized by the Williamson procedure. The Williamson ether synthesis is an organic reaction forming an ether from an alkyl halide and an alcohol. This reaction was developed by Alexander Williamson in 1850. As said, it involves the reaction of an alloxy ion with a primary alkyl halide via SN2 reaction. And the Williamson reaction is a widely used in both laboratory and industrial synthesis and remains the simplest and most popular method of preparing the ether. Here we can prepare both the symmetrical and asymmetrical ether by the Williamson ether synthesis. So, the Williamson ether synthesis involves the reaction of a sodium aloxide, that is RONA, or a sodium phenoxide, that is ARONA, with an alkyl halide to form an ether. And here the reaction involves a nucleophilic substitution of an aloxide ion for an halide ion. So this is the general representation for the preparation of the ether. So either sodium aloxide or sodium phenoxide can be taken depending on the type of the ether which we require, and when they are made to react with an alkyl halide, we get the corresponding alkyl ether or an aryl ether. Let us take a few examples. So here I am going to take CH3CH2Br, that is ethyl bromide. When it reacts with the sodium aloxide, that is the ethyl aloxide, here we are going to get diethyl ether as the product. So when I use a sodium phenoxide and a methyl halide, that is methyl iodide, I here get is methyl phenyl ether as the product. So let us learn in detail about the Williamson ether synthesis. So as I said, when an alkyl halide is allowed to react with a sodium aloxide, a symmetrical or an unsymmetrical ethers are formed, and the general representation is RONA plus R dash X will give rise to ROR dash plus NaX. So here I have taken example for a aloxide as well as a phenoxide. So when I take a sodium aloxide, I get the corresponding alkyl ether. When I take the sodium phenoxide, I get the aryl alkyl ether. As said already, when a sodium aloxide reacts with an alkyl halide, we get the alkyl ether, and when a sodium phenoxide is made to react with an alkyl halide, we get the aryl alkyl ether. Coming to the steps or a few examples for your Williamson ether synthesis. So here the first step will tell us how a sodium aloxide is being formed. So here we take an alcohol and made it to react with the sodium. Here correspondingly sodium aloxide is being formed. And this sodium aloxide, for example, when I take to be the sodium ethoxide, so here I take the ethyl alcohol made to react with the sodium, and I get the sodium ethoxide. It is made to react with the bromoethane. I get the simple ether, diethyl ether. So the other example here I'm going to take is for an unsymmetrical ether. So instead of sodium ethoxide, I'll be taking sodium tertiary butoxide and made to react with the bromomethane, and here I get a tertiary butyl methyl ether, an example for an unsymmetrical ether. And to get an alkyl aryl ether, I'll be using the sodium phenoxide and an alkyl halide. So as seen in this equation, if I take the corresponding aromatic alcohol, that is the phenol, and made to react with the sodium, I get the sodium phenoxide. The sodium phenoxide is made to react with the bromomethane, that is an alkyl halide, and correspondingly here we will be getting the methoxybenzene. So here it is an unsymmetrical, and it is an example for an aryl alkyl ether. Coming to the mechanism of Williamson ether synthesis, as we had discussed, it involves the displacement of a halide ion from an alkyl halide, and hence we call it to be a nucleophilic substitution by an alkoxide. And here it is going to follow the SN2 mechanism. Let us look into the steps which is involved in the Williamson ether synthesis. The step 1, here the alcohol reacts with the sodium metal to form the conjugate base sodium alkoxide and releases the hydrogen gas. So here we are getting the alkoxol, sodium alkoxide in the step 1. The sodium alkoxide which is being obtained in the step 1 is added to a primary alkyl halide to form the desired ether along with the sodium halide. So here the alkoxide is made to react with an alkyl halide. So here there will be a substitution of a halide group by an alkoxide, and since it is a nucleophilic, we call it to be a nucleophilic substitution, and here it is a simultaneously formation of a bond and a removal of an halide. We call it to be the SN2 mechanism. So here the product that is obtained is the ether ROR and a sodium halide is formed. So it involves two-step formation of a sodium haloxide which in turn reacts with an alkyl halide, undergoes a nucleophilic substitution to give the ether. However, there are certain limitations for Williamson ether synthesis. So, as we had discussed in the previous slide, in Williamson synthesis for the preparation of ether, haloxide ion act as a nucleophile and attacks via SN2 mechanism to a primary alkyl halide, or generally we take to be a methyl halide. However, when a secondary or a tertiary alkyl halide is used instead of a primary alkyl halide, along with the substitution, elimination is also possible. So we know whenever there is an combination, it gives rise to an alkenes, and alkene as nucleoside alkoxide ion is a nucleophile. They can also act as a strong base. Hence, they react with alkyl halide, which results in the elimination reaction, which is one of the limitation of the Williamson ether synthesis. So here I have given the representation. So whenever we take a secondary or a tertiary alkyl halide is used, so rather of getting an ether, there are a chance of being getting going for an elimination reaction, and an alkene product is formed, and this is one of the limitation of the Williamson ether synthesis. Coming to the next limitation of the ether synthesis, here since a halogen attached to an aromatic ring cannot be readily replaced by a nucleophilic reagent, aryl halides are not generally used in the Williamson synthesis. Therefore, in the preparation of an alkyl aride ether, the reaction is always carried out between an alkyl halide and a sodium phenoxide, and not between an aryl halide and a sodium alkoxide. And this is the second limitation for the Williamson ether synthesis. And in Williamson ether synthesis, diaryl ethers are not generally prepared by this reaction. And these are the references for this PPT.